As a last example of polar coordinates, I'd like to show you one of my favorite integrals. This is one which doesn't look like a Cal3 integral at all, the integral from negative infinity to infinity of e to the negative x squared dx. But it turns out I don't know any calculus 2 techniques that allow us to figure out what it is. Now the graph of the function y equals e to the negative x squared is kind of important. If you graph it, it has this shape, which might remind you of what's called the bell curve. And in fact, the bell curve in statistics is based on this function. There's an extra constant up here to adjust it so that we have an area of 1 underneath the curve. So let's see if we can figure out what this is. The first thing I'd like to do is to rewrite this as twice the integral from 0 to infinity e to the negative x squared dx. Notice that this function is symmetric across the y-axis. If you replace x with negative x, the function's unchanged. So this is something legal. Now, something that we will need to deal with a little bit later is that since this is an improper integral, one that's going out to infinity, remember back from Cal 2, that we'll replace this with the limit as b goes to infinity, integral to b of e to the negative x squared dx. So we integrate out to b, get a formula involving b, and then we'll let b go to infinity. That'll be something to deal with a little bit later in the problem. So if I call this original integral I, then I have that I is equal to twice the integral from 0 to infinity e to the negative x squared dx. Now, if I were simply to change the x's to y's in this, that wouldn't change the value of the integral. So I could also say that I is equal to twice the integral from 0 to infinity e to the negative y squared dy. That didn't seem to accomplish much. But now let's multiply these together. That will tell me that I squared is equal to 4 times the integral from 0 to infinity e to the negative x squared dx times integral 0 to infinity e to the negative y squared dy. And I want to use that trick of taking this product and putting it into a single integral. So we're running the trick that we've done before backwards. Instead of writing it as a product, I'm going to combine these two into a single integral, dx dy. And on the inside, I'll multiply the e to the negative x squared and the e to the negative y squared. So that gives me e to the minus x squared minus y squared. So what we have so far is that our integral squared is 4 times the integral 0 to infinity, integral 0 to infinity, of, let me rewrite this as e to the negative x squared plus y squared dx dy. Now what region am I integrating over in the xy plane? Well, y is going from 0 to infinity, so I'm staying above the x-axis. And x is going from 0 to infinity, so I'm staying to the right of the y-axis. So that means that, thinking about this now as a double integral, I squared is equal to the double, 4 times the double integral of e to the negative x squared plus y squared over this region R, where R is the first quadrant. Interesting. Notice, though, that with this x squared plus y squared, that gives us the idea that we might want to use polar coordinates to carry out the integral. That turns out to be a really good idea. Now, in polar coordinates, dx dy becomes r dr d theta. And e to the negative x squared plus y squared is e to the negative r squared. Now notice that if you had tried to use a u substitution here to do this integral, you would set u equal to negative x squared, and du would be negative 2x dx. And there's no x dx. That's why we couldn't do this in Cal 2. Down here, though, if I set u equal to negative r squared, then du is negative 2r dr, and now we have an r dr. Let me recopy what we've got so far. We have that I squared is equal to 4 times the integral of e to the negative r squared times r dr d theta. And let's set up our bounds. Notice that r is going to go from 0 to infinity, and theta is going to go from 0 to pi over 2. Here's theta equals 0. Here's theta equals pi over 2. And for any angle in between, r is going to start at 0, and it's going to go out to infinity. So saying with the bounds, theta is from 0 to pi over 2, and r is 0 to infinity. Now here, if we like, we can split this up. These aren't constants at the moment. We're going to set theta equal to b, and then we're going to have a nice rectangle. And then inside, I've got a function of r, and the function of theta is just 1. So I have 4 integral 0 to pi over 2 of planal d theta multiplied by the integral 0 to infinity e to the negative r squared times r dr. This first integral is straightforward. This is 4 theta taken from 0 to pi over 2, which is just going to be 2 pi. So this first integral is done. This second one we now need to write as the limit as b goes to infinity, integral 0 to b, e to the negative r squared times r dr. And now we'll do that u substitution I mentioned. If we let u equal negative r squared, du is negative 2r dr. So I'll multiply by a negative 2 and divide by negative 2. And then the integrand is going to become e to the u du. So here I have a negative 1/2. Limit as b goes to infinity. Integral of e to the u du. I'm not going to switch bounds. I'll switch back to r's in a moment. So 2 pi times negative 1/2 is negative pi times the limit as b goes to infinity. The integral of e to the u is just e to the u, taken from something to something. And now let's switch back to r's. I'll have negative pi times the limit as b goes to infinity of e to the negative r squared taken from r equals 0 to r equals b, which is negative pi times the limit as b goes to infinity, e to the negative b squared minus e to the 0, which is 1, let's simplify just a little bit more before we take that limit. That's negative pi times the limit as b goes to infinity of 1 over e to the b squared minus 1. As b goes to infinity, this denominator is going to 0 while the numerator is constant, which means that this limit is 0. So I have negative pi times negative 1, which is pi. Don't jump to a conclusion quite too quick. Remember, this is not the value for I, this is I squared. So the square of the integral we're looking for is equal to pi. So that means that the area under the curve I is equal to the square root of pi. So the conclusion we can draw is that this very interesting integral has a value square root of pi. So if you look in a statistics book for the formula for the bell curve, you'll notice that there's a pi up there, an adjustment of pi up in the exponent, so that the area ends up being 1 instead of the square root of pi.